Good day, everyone. So today we're going to talk about a topic back in section 12.1. In my opinion, the textbook mentions this way too early, and so I'd like to go through some actual hypothesis testing. So basically, we are moving back a section back into 12.1 and talking about type 1 and type 2 errors. Now, the very first folks that came up with this decided to use Roman numerals, and uh, and so you'll see that a lot in the textbook. Uh, that they're going to use Roman numerals. That's why you see my title as it is, but certainly you can use standard numbers. So we have to come to this realization is that with hypothesis testing, since we're using data from a random sample, okay, and the word to concentrate here is on the word sample, and we didn't get our data from a census. We didn't look at all the data, all right, just part of it, all right. Basically, we have incomplete data. And no matter our final conclusion, it doesn't matter if you reject the null or do not reject the null, we could be wrong. And so since we could be wrong, all right, we want to know basically how often are these going to happen, okay? And and we should certainly talk about these things. That okay, so most of the time we will make the correct decision, okay? But every once in a while, by chance. So when do these happen? And why do they happen? Well, they happen by they happen random. They happen by chance. Okay, so you didn't do anything wrong. So the word error doesn't mean that something that you did wrong or a researcher did wrong. Okay, it just happened by chance. Okay, either one of these errors. So what is a type 1 error? The definition that you'll see in a textbook is rejecting a true null hypothesis. To be honest with you, I'm not fond of that definition. I like to think of it in terms of the alternative. And so if you think of it that way, basically, okay, so we rejected the null, right? So if we reject the null, we think the alternative is correct. So we thought that the alternative HA is correct. Oh, but we were wrong. Simple as that. The media will call these false positives, and you've been hearing about false positives a lot, especially with the whole coronavirus. False positives. Okay, so we'll talk more about false positives and how they are type 1 errors. But truly, when you hear about a false positive, they're talking statistics. They're talking about a type 1 error. It's just that the media knows that a bunch of people haven't taken a stats course before, and so they got to talk about it in a certain way that they could maybe possibly understand. And so they have sort of adopted the way that the medical field thinks of it. All right, the medical field thinks of it, type 1 error, as a false positive. All right. Type 2 error, not rejecting a false null hypothesis. All right. Not rejecting a false null. And so I like to put it in terms of H sub A. So what does that mean in terms of H sub A? We could not conclude the alternative is correct. Oh, but it was. So we couldn't conclude HA, but we should have. All right. Media will call this a false negative. False negative. All right, so here's a real life example. Believe it or not, a pregnancy test is a clear cut indication of how to link type 1 errors and false positives, type 2 errors, and false negatives. So a female takes a pregnancy test, and generally speaking, what's going to happen with that pregnancy test? It's either going to give you a plus sign or a minus sign. Plus sign means she's pregnant, minus sign says she's not. Okay? So positives, negatives. Okay? All right. So believe it or not, a pregnancy test is basically a hypothesis test, where the null hypothesis is that she's not pregnant. It's the status quo of the female. And H sub A is that she is pregnant. Change from the status quo. So is it possible that a pregnancy test gave wrong results? I mean, let's face it. Um, uh, I'm sure you've heard of a female taking a pregnancy test and getting the opposite of what she was hoping for. And so what she might do? She might take another one, right? Or go visit the doctor and certainly have it confirmed at the doctor's office, all right? But the thinking is that, oh, maybe the test was wrong. Well, okay, that's what we're talking about here, right? So a type 1 error, again, there's the definition, but we're going to put it in terms of H sub A, maybe. Maybe that's the better way of thinking. So a type 1 error in terms of the problem for this particular problem would be the following. So remember, we rejected the null. So we thought HA was correct. So we thought that, or at least the test thought, that the female was pregnant, but in reality, she wasn't. Simple as that. So we rejected the null. Okay, we rejected the null. All right, so we thought she was pregnant, or the test thought she was pregnant, but she wasn't. Now, the way you got to think of it with regards to a false positive is that a positive isn't necessarily a good thing. Okay, it's not necessarily a good thing because a female being pregnant might be a good thing for her or a bad thing, uh, depending on her time of her life. All right, and so what does really a plus mean? Plus means that whatever we were testing for, the test detected it. So the test was trying to detect if she was pregnant. All right. And so a plus means that whatever we were testing for, whatever effect we were testing for, it detected it. So that means a false positive is that the test detected an effect, but it wasn't present. False positive. All right. All right. How about a type 2 error? Not rejecting a false null, right? We'll try to put it in terms of H sub A. So let's go ahead and define a type 2 error in terms of the problem. So we couldn't conclude the female is pregnant, but in reality, she was. All right. So remember, we don't accept the null as being true. And so the best way to say this then is that we couldn't conclude the female is pregnant. All right. But in reality, she was. All right. So we couldn't conclude HA, but in reality, she was. Okay. And so a negative is not necessarily a bad thing. Okay. Negative means whatever we were testing for, test it, detect it. So that means a false negative is that the test didn't detect an effect. Oh, but it was present. Okay. False positives, type 1 error. False negatives, type 2 error. So in this class, since we are talking statistics in general, we should talk about it in type 1 and type 2 errors. But certainly we should be able to relate to what the media is talking about. And certainly when you go to the doctor's office and they talk about false positives and false negatives, you'll have a good understanding of it. Okay. All right. So here's a problem. The Federal Reserve is constantly sampling U.S. households about how much money they have in savings for rainy days. And so let's say that we're going to test if mu is equal to $12,000 and the alternative mu is greater than $12,000. So how much on average U.S. households have in savings? All right, so what would be a type 1 error in terms of the problem? So based on our test, okay, so we ran through the test, we rejected the null, we thought the alternative was correct. So in other words, we thought mu was greater than 12,000. So we thought that the mean savings for all U.S. households is greater than 12,000, but in reality it wasn't. Okay. By the way, don't say that, but in reality it was 12,000. Okay. It could actually have been less than 12,000. All right. So I would just put it the way I put it here. Okay. It covers everything. All right. How about a type 2 error? Not rejecting a false. All right. So define a type 2 error in terms of the problem. So based upon our test, we couldn't conclude that the mean savings for all households is greater than 12,000, but in reality, it was. So we couldn't detect to go ahead and say that mu was greater than 12,000. But it was. Type 2 error. Okay, not rejecting a false null. But again, I prefer to think of it in terms of H sub A. So we couldn't conclude HA, but we should have. All right, so we should talk about how often these things occur. So the probability of making a type 1 and type 2 errors. Okay, So the first place to start with this is that who chooses the level of alpha? And the reason why, uh, well, we'll get to that in a second, why we have to talk about that. But the researcher, or most likely the industry that the researcher's in, is going to choose alpha. Now, why is that important here? Is because the probability of making a type 1 error is alpha. It's the significance level. All right. So I'm not saying a type 1 error is alpha. I'm saying the probability of a type 1 error is alpha. The probability of making a type 2 error is what we call beta. Beta. All right. So we got alpha and beta. Beta as a calculation is beyond the scope of this course. I used to go over it, but students got their shorts kind of tied up a little bit when doing the calculation, and so I've kind of skipped over that. Your next stats course, I'm sure we'll go over the calculation for beta. All right. But here's the thing, is that what we should understand is that alpha and beta are inversely related to one another. All right. So if a researcher increases alpha, beta automatically decreases. So in other words, if the researcher starts at, say, an alpha of 0.01 and then increases alpha to 0.05 without doing anything else, beta automatically decreases, and vice versa. Now, it doesn't go up and down proportionally, all right? So on this second sentence here, it says if a researcher decreases alpha, beta automatically increases. So that's important, all right? Now, what does this have to do with going back to industry standards and so on and so forth? Well, because the researcher, or the industry for that matter, has to say, okay, what errors should we usually protect against? Okay, and we'll go through some calculations and make sure that alpha and beta are reasonable numbers. All right, and so we don't want to make alpha too small because that's going to make beta too high, and we don't want to make uh, alpha too high. Okay, uh, as we know, because that has everything to do with rejecting the null hypothesis or not. And so that's why a lot of times industries have set on a 0.05 for alpha, because it sort of says this is a good balancing point between alpha and beta, is this 0.05. Okay, I can't get in any more into it without going through the calculations for beta. Okay, um, but that's the reasons why usually industries have set on 0.05. So a doctor orders a test to determine if a patient has cancer. So the null is the patient does not have cancer. It's the status quo of the person. All right, HA is patient has cancer, unfortunately. So type 1 error, test indicates cancer. Okay, so remember, rejecting the null, thought the alternative is correct, so the test indicated cancer, but in reality, no cancer is present. Type 2 error. Test did not detect cancer, but in reality, cancer is present. Okay, so I got a question for you. In your opinion, which is the worst error? And if we were in class, we would have this discussion. Some people do say a type 1 error, but most say a type 2 error. In this situation, most people say a type 2 error. And so the people who say a type 1 error, they say, well, because if the person has cancer, they'll start getting chemo and other treatments unnecessarily. All right. And then for people who say type 2 errors is the more damning error, that so the person has cancer but is not getting treated for it, and it might be going into later stages and might get past the point where the patient can't recover. All right. And so early detection is the best thing. Okay. And so the medical field sat down and said, well, which one is the worst error to them? To them, a type 2 error is the worst. Okay. They don't want a person to have cancer and not get treated right away. So, so what about the people that said type 1 error? Well, the way the medical field tries to protect against the type 1 error is that they run multiple tests. And so, let's say that you went to your general physician, You didn't feel good. You said, man, this part of my body is just constantly hurting. They check it out, and um, uh, and the test seems to be indicating cancer. Are they just going to go straight to um, giving you chemo at that point? Probably not. The general physician then is probably going to send you to a specialist. And then the specialist is going to run at least one more test, probably multiple tests to check for cancer in these multiple tests. And to keep on having multiple tests time after time after time to say cancer when there really is no cancer present, and it's probably not going to happen too often then. Okay. So that's the way the medical field protects against a type 1 error, is that they just keep on running some tests. Okay. Until they're pretty sure that the person really truly has cancer. Okay. And so, so this is why, you know, it's important that we set alpha and for that matter, beta at a good, reasonable level. So the last thing I want to talk about is power. All right. Power is the probability of accepting the alternative hypothesis as true when it actually was true. So in other words, that we rejected the null when we should have. Okay. And we accepted the alternative when we should have. All right. That's what we call power in statistics. Power is equal to 1 minus beta. So power is equal to 1 minus the probability of making a type 2 error. All right. That means a low power suggests a high beta. A high statistical power suggests a low beta. Okay. And vice versa, if you will. So it is common for researchers to design experiments that have power greater than 0.8. Okay. So they want the power to be greater than 0.8. And sample size is directly related to statistical power. All right. So one way to lower beta, other than messing around with alpha, is to increase the sample size. All right. Now the calculation is beyond the scope of the course, so you'll have to kind of accept that one. Therefore, if the sample size is increased, that lowers beta, which increases the statistical power. Okay. Now, do we want crazy high sample sizes? No. Sometimes we do have to control it, okay, and make it a reasonable number, just like we saw with confidence intervals. We have to make it a reasonable number. And so basically, often researchers will ask statisticians to do a power analysis. So they want to know, where should we set n to do a confidence interval, to do a hypothesis test, to have the power to be high enough, okay, so that beta uh, isn't too high, okay, and again, this is all making sure that probably we have alpha set to 0.05, okay, and so there's a lot of analysis that goes into that. And so a lot of times a researcher will ask a statistician to do this power analysis to make sure that that these things, the power and the beta and the alpha are all sort of matching up and at reasonable levels. Okay. All right. That's the end of our presentation. Thank you for your time.